This webcast talks about problems that involve elastic potential energy stored in a spring. And so I'm working in worksheet 6D. The first problem says that Maggie and her team, they've conducted an experiment with a spring that's been fabricated from a new metal alloy. And here are their results. So we've got a table that shows the displacement of the spring and how much force it took to cause that displacement. And this is a graph of the applied force versus the displacement of the end of the spring. They're asking us for the spring constant. So I'm going to use two values in the table to calculate the spring constant. So I'm just going to choose the first and the last. And the slope of this force versus displacement graph equals the spring constant. And so I'm going to have 453.9 minus 0. That's my y2 minus y1. That's the force, and it's measured in newtons. And then my x2 minus x1 is going to be 102 minus 0, and that's measured in centimeters. Pay attention, that's centimeters, but it's asking me to give the spring constant in newtons per meters. Okay, so after I calculate this, I'll convert centimeters to meters. So I have 453.9 divided by 102. So my spring constant is 4.45, but that's newtons per centimeter. And I know that that 1 centimeter is 10 to the negative 2 meters. And so I need to convert, and that will give me a spring constant of 445 newtons per meter. Okay, what does this spring constant mean? Since it's a slope, I'm going to explain it the same way that I do for slopes. So I'm going to start with for every additional. And it's for every additional 1 unit of the independent variable. My independent variable here is the displacement of the end of the spring. So for every additional 1 meter, I'm using meter because I have converted my slope to meters, newtons per meter instead of newtons per centimeter. So for every additional 1 meter of displacement of the end of the spring, okay, so I've explained 1 unit of change of the independent variable. Now I want to explain how the dependent variable responded. So the force, or the applied force, increased by 445 newtons. Okay. So how much force must be applied to the spring to stretch it by half a meter? Well, so here I really kind of need a physics equation, right? Which is that the applied force equals the 445 newtons per meter multiplied by the displacement of the spring. And this is a formula we need to know. The applied force equals the spring constant times the displacement. Okay, so I'm going to plug in. I've got 445 newtons per meter, and they're giving me a displacement of half a meter. And so that would be 222.5 newtons. That's how much force it would take to displace it by half a meter. Okay, and it says, okay, so then how much energy would be stored in the spring when it's been stretched by half a meter? And this energy, it says to show it 2 ways. One is graphically using the graph above, and the other is algebraically. In the lab that we've done, I know that there's an equation that says the elastic potential energy is half of the spring constant multiplied by the displacement squared. So I can calculate it algebraically. It would be half of the 445, that's the spring constant, multiplied by the displacement squared. And so that would be 55.625, and the units of energy are joules. On the graph, if it's been displaced by half a meter, that would be 50 centimeters. Okay, I'm going to just kind of pencil in, if you will, the line here for this graph. And so the energy is the area under the graph. So this area that I'm shading in, this is the energy stored when the displacement is half a meter. Okay, so to show the energy stored in the spring, it would be the area between the force versus displacement graph and the x-axis. Okay. Then it says if the spring was already stretched by half a meter, but then it gets stretched even further to 0.6 meters, how much additional energy would be stored in the spring? I'm kind of talking about what's the difference between the energy stored when the spring is stretched by 0.6 meters and the energy when the spring is stretched by half a meter. So I'm looking for the change in that elastic potential energy. It would be the energy stored at 0.6 meters of stretch minus the energy stored at half a meter of stretch. Let's go look at the graph again. So if this green triangle is the energy that's stored when the displacement is half a meter, this red triangle, if you will, is the energy stored when the displacement is 0.6 meters. And so the difference between these, I'm going to shade in this green highlighter color. That difference between the red triangle and the green triangle is the additional energy that gets stored. Notice the shape of that. That is a trapezoid. And so, so anyway, we're going to be finding the area of that trapezoid. But so the energy stored when the spring is stretched to 0.6 meters would be half of the spring constant multiplied by 0.6, that's the displacement squared. And the energy stored when it is stretched by half a meter is half of the spring constant times 0.5 squared. We already calculated that above, right? But if I take the difference between these, I get 80.1 joules when it is stretched to 0.6 meters, and I got 55.625 when it was stretched to 0.5 meters. And so the difference there, if I just subtract, is 24.475 joules. That's how much, that's how much additional energy is stored when it is stretched that little bit of additional distance. Okay, How far would the spring have to be stretched to store 64 joules of energy? Well, the relationship between being stretched and how much energy is stored is that the change in, or is that the elastic potential energy, sorry, let me do that. Elastic potential energy is half of the spring constant multiplied by the displacement squared. Well, here I know the amount of the energy that's stored. I want it to store 64 joules. And I know the spring constant, because we calculated it's 445. So what I'm solving is for the displacement, right? That's the thing I'm solving for. So the displacement would be 64 divided by 1/2 and divided by 445. I'm just moving those to the other side. And I want displacement. I don't want displacement squared. So I have to take the square root of that. And so when I calculate, it would have to be 0.536 meters. Okay, let's go into number 2. Now we've got two springs, and they have different spring constants. One has a K of 300, the other has a K of 600. If they are both stretched by the same amount of applied force, on which spring has more work been done? In other words, which spring is storing more energy? So for spring A, the energy that's stored would be 1/2 of the K times the delta X of spring A squared. Can I find the delta X of A? I can, because I know that the applied force equals K delta X, which tells me that the delta X is the applied force divided by the K, right? So for spring A, that would be 100 newtons divided by 300. So it would be 0.333 meters. Okay, so the energy in A would be half of 300 times 0.333 squared, which would be 16.633 joules. Okay, the energy stored in spring B, so I'm going to have to find the displacement for spring B. It would be 100 divided by 600, right? 100 newtons divided by 600 newtons per meter, which would be 0.167 meters. It's not, it has a stiffer spring constant, and so the same amount of force is going to cause a smaller displacement for it. But let's see how much energy is stored in it. So I have half of the spring constant, 600, times the displacement squared. That's 0.167 squared, and I get 8.367 joules. So more work was done on spring A. In other words, more energy was transferred to spring A, which has a smaller spring constant, when I applied the same amount of force. Okay. And then the last problem here takes 20 newtons of force to hold a spring stretched to a distance of 40 centimeters. Okay, so the first thing we're going to have to do is find the spring constant. So I know that applied force equals the spring constant times the displacement. So if they're saying 20 newtons of force cause a displacement, and this is 40 centimeters, we've got to put that in meters. That would be 0.4 meters. Then the K is 20 divided by 0.4, which is 50 newtons per meter. You have to work in standard units. Okay, then what is the elastic potential energy of the spring at that position? Well, the elastic potential energy is half of the spring constant times the displacement squared. So I have half of 50 times the 0.4 squared. So let's see here. So that would be 4 joules. When the spring is released, what will be the amount and direction of the spring force? So the spring force is negative K delta X. And so that would be negative 50 times 0.4. So it would be negative 20 newtons. And the negative means to the left. So if it takes 5 joules of work to stretch a spring 20 centimeters, how much additional work must be done to stretch it an additional 15 centimeters? The relationship here is that elastic potential energy is half of the spring constant times the displacement squared. I don't know the K yet, but this first sentence here, that it takes 5 joules to stretch it 20 centimeters, would, I think, let me find K, because 5 joules of energy would be taken to stretch it 20 centimeters. Be sure to convert the 20 centimeters to meters. So then K would be 250 newtons per meter. Okay. So the additional work would be the difference between the elastic potential energy stored at 20 centimeters. Oh, I'm sorry. So first it was stretched 20 centimeters, and then it stretched an additional 15. So then the total is 35 centimeters, right? So I need to take the difference of the energy stored when it's at 35 centimeters minus the energy stored when it's at 20 centimeters. Okay? So the energy stored at 35 centimeters is half of the K, 250, times the 0.35 squared, right? That's the displacement squared, minus the energy stored at 20 centimeters, which was 5 joules, right? They've already calculated that for me. And so that's 45 minus 5. So the additional energy, or the work that would have to be done, would be 40 joules of work.